Hello, my name is Kaylie Barber. I am a rising third-year student at the Pennsylvania State University studying mechanical engineering and mechatronics in the Schreier Honors College. This summer, as part of the Robotics Institute for Summer Scholars, or RIS program, I had the privilege to work under Dr. Zainab Tamel and alongside my twin sister, Kaylie Barber, to design an origami bistable swimming robot. I'd like to share with you a dive into origami, an exploration of the propulsion of YoDiFin, a swimming robot. For some background, we looked at bio-inspiration. From the undulatory motion of fish to the jet-like propulsion of sea scallops, nature has so many different ways that it goes about swimming. Our mechanism uses a jet-like propulsion similar to that of sea scallops to propel itself forwards in the water. In order to swim, one must break symmetry to cause propulsion in a dominant direction. This can be either time symmetry by adjusting something like actuation speeds, or it can be shape changes to cause configuration symmetry to be broken. This project used origami, which is an ancient art of folding paper. Although initially just an artistic form, origami is now being used in engineering to achieve different geometries and motions within mechanisms. For propulsion, this mechanism uses what we developed as a diamond fin design. This was initially developed using origami paper and folding to allow for fast and iterative prototyping. It was then imported into CAD to be able to optimize the dimensions to achieve the desired movement. We combined this diamond fin design with a YoDiFin design, which is the actuation mechanism. YoDiFin is pushed down by a servo motor, thereby closing the fins of diamond fin. And then when the servo motor releases YoDiFin, the bistable design allows it to spring open and open up the fins of diamond fin to be able to swim. These mechanisms, diamond fin and YoDiFin, combine to make one swimming robot, YoDiFin. To manufacture this robot, we used a process called lamination. In lamination, we combined rigid, adhesive, and flexible layers together to allow for a restricted amount of movement. We can cut the rigid and adhesive layers at certain points, leaving only a flexible layer to create joints. The mechanism then bends along these joints to achieve the desired motion. These layers were assembled together using an acrylic board and pins to make sure they were aligned properly, and then folded into the 3D structure and glued in that structure. The final mechanism, YoDiFin, is 160 by 260 by 65 millimeters with 130 millimeter long fins. Just the mechanism alone weighs about 45 grams, and it weighs 105 grams with the actuator. Next, we wanted to put this robot in the water. So we tested it in a tank of water with about a 38-liter capacity. To make our mechanism float, we added foam to achieve the buoyancy. That way it was able to travel the length of the tank, staying in the surface of the water. It was able to propel itself forward at 2.1 centimeters per second using that jet-like movement that I mentioned earlier. As the fins are brought together, it creates that jet and moves the robot forwards. And then when it's released, the bistable design springs the fins back open so that the robot is primed and ready to complete its next actuation cycle. Although it is using this jet propulsion motion, that is not initially what it was designed for. When we first designed the robot, we expected it to close its fins slowly, and as it opened them with the bistable snap, to push itself in the opposite direction in the water. So because it's exhibiting motion we did not expect, we would like to create a mathematical model or a simulation to better characterize this motion to determine if perhaps using a different actuation system could cause the mechanism to move how we initially designed it to. For control, diamond fin has the capability of single fin actuation, whereby only one fin would be moving, opening and closing to allow the robot to turn. So we would like to improve the actuation system to allow for that. Furthermore, having more control over the actuation will also allow us to adapt the robot's speed as it could open and close slower or faster. Applications of this robot can include underwater discovery, as this robot is rather small and quite flexible and durable that it could go into different locations. It is also a great example of mechanisms working together and could be used in an educational setting to understand how compliant mechanisms work. This is a video of YoDiFin in action swimming across our tank. You can see the motor pushing on the YoFin portion, causing the diamond fin portion, the fins to close and open, propelling it forwards. I would like to take a moment to thank the RISC program for this amazing opportunity to research at Carnegie Mellon University. I learned so much about robotics and got to collaborate with so many scholars from across the globe and connect with professionals in the robotics field. It has really opened opportunities in the robotics field for me, and I'm grateful to have worked on this project. Thank you.